Now let us look at more detailed of the response to a single complex 0. So by response we mean magnitude frequency response. So we have each of z to be 1 minus r e to the j theta z inverse. Therefore, you have a non-trivial 0 at r e to the j theta, and the magnitude squared frequency response is given by 1 minus r e to the j theta e to the minus j omega whole squared, and this you can write it as this times its complex conjugate. So this can be written as 1 plus r squared minus 2r cos omega minus theta. This is easily verified. So this is the algebraic expression, and if you plot the frequency response, note that the 0 is fixed. So r and theta are fixed known quantities. The only variable in this expression is omega, and omega goes from 0 to 2 pi or between minus pi and pi. In terms of pole 0 plot, you have a trivial pole and then you have a non-trivial 0. This radius is r, the angle is theta, because the 0 is at r e to the j theta. On a linear scale, if you plot this, this will look like what function? Yeah, this will look like a simple cosine because the only variable here is omega, and this will look like a shifted cosine depending on the parameters. But we will, as I had mentioned, we will plot all these things on a log scale. And if you look at this on a log scale, so if you are here on the unit circle, you might have a certain magnitude response, and then when you go along, you are going to approach this 0, and hence the response will fall. And when you are exactly at the same angle as the angle of the 0, that is when omega equals theta, you will be closest to the 0. So you can expect the response to have a minimum value at that particular frequency, and hence the response will have a minimum value at omega equal to theta. When you go past the 0, the response is going to increase, and then when you cross the 0, the response is going to increase, and then when you are exactly at the opposite frequency value compared to the location of the 0, that is when omega equals, what value will this be a maximum? Theta plus pi. At omega equal to theta plus pi, you are farthest away from the 0, and hence you can expect the response to be maximum. And then when you complete the circuit around the unit circle, you will reach exactly the same value at 2 pi, which corresponds to the value at omega equal to 0. So this is the frequency response of a single complex 0, that is log magnitude. So this is typically 20 log 10 magnitude of h of e to the j omega. Note that h of e to the j omega whole squared minimum will occur when omega equals theta. Therefore, when omega equals theta, this becomes 1 plus r squared minus 2r, and hence the minimum value magnitude squared is 1 minus r whole squared. And the magnitude squared has a maximum when omega equals theta plus pi, or when omega minus theta equals pi. When omega minus theta equals pi, this becomes 1 plus r squared plus 2r. Therefore, this becomes 1 plus r whole squared. So, note that on a linear scale this will be precisely a cosine, but on a log scale you have this, and all our qualitative description of the frequency response will be based on the picture that we see on the log scale. And you see that on the log scale, this is the valley, this is contributed by the 0. Therefore, this valley is sharp, and this is the peak, and the peak is broad. So, we make the general statement that zeros close to the unit circle give rise to sharp valleys. And you can easily see this in MATLAB. So, we are going to use the freq z function. So, H is the function that is going to have the complex frequency response. So, this is freq z. Freq z takes the format b comma a comma n. B is the numerator coefficient. Let me take the radius to be 0.9. So, 1 minus 0.9 z inverse is the numerator polynomial, because I have taken r to be 0.9, and then I can make the angle to be pi by 4. So, j times pi by 4. So, this is the numerator polynomial. Denominator polynomial is 1, and then I am going to evaluate this at 2000 points. In general, freq z assumes that b comma a are real valued. So, if you do not give any additional argument, it will evaluate the frequency response at 2000 points from 0 to pi, because it will assume b and a are real valued, whereas in this case we have complex 0, and hence we want to evaluate the frequency response from 0 to 2 pi. So, 0 to 2 pi, 2000 points are going to be used for evaluation, and then I have to say whole. So, this is the frequency response of this particular simple minded system, and now I need to plot the magnitude response. So, let me plot the magnitude response on a linear scale. So, if I plot, since I have taken 2000 points, I want to normalize the x axis to be between 0 to 1. We have evaluated the response from 0 to 2 pi. If you divide by 2 pi, the interval becomes 0 to 1. Therefore, I will take 2000 points and then divide by 2000, so that the interval becomes 0 to 1, and then I will plot the absolute value of the frequency response. Now, this will look like a cosine. Really what I have done is I have plotted the magnitude. What looks like a cosine is the magnitude squared, right. Therefore, this does not look like a cosine because this is the magnitude of the transfer function. What is the cosine? Is the magnitude squared. So there is the magnitude squared, which looks like exactly like a cosine. Now, what we really want is, we want the log magnitude, and we plot 20 times log 10 of the magnitude response. And here you see a plot that is similar to what I had sketched roughly based on the geometric interpretation. So the actual response is this, and you can see here that the valley is sharp, the peak is broad, and we are making these descriptions based on the log magnitude response. And the angle is pi by 4. So pi by 4, when you divide by 2 pi, is 1 over 8, and 1 over 8 is 0.125. Therefore, you see here that this dip occurs exactly at 0.125, and this peak will occur at pi by 4 plus 2 pi by 2 pi. All right. Therefore, the locations of the peak and the valley are at expected places. And because the radius is 0.9, right, and the minimum value is 1 minus 0.9 whole squared, which is 0.01, and that is minus 20 dB. So all these numbers are also corresponding to what they should be. No surprises here. Therefore, this is the precise plot, and this is the rough plot. Moment you have the response of a single complex 0, response of a single complex pole is trivial. So now you have h of z to be 1 by 1 minus r e to the j theta z inverse, and the log magnitude plot of this will be just the negative of this. Once you have the log magnitude of the 0, the log magnitude response of the pole is just the negative of this, and hence, without repeating what was the equations that I've written earlier, let me just plot the qualitative picture. So this is how the picture will be, and what was the valley before has now become the peak. So now this becomes the peak and is sharp, and this valley is broad. And the same for the same parameters, if I plot in MATLAB, the response will be just the previous plot, but for a minus sign. So this gives you a feel for the response of a single complex pole and single complex 0. So we saw the qualitative plot, and you have also seen the exact plot. And carrying this further, we can look at responses of crude low pass and high pass filters, and we can realize crude low pass and high pass filters either using a single 0 or a single pole, and then we'll see the differences in the responses. Let me first draw the qualitative picture. Suppose I have a pole here, By the way, this goes both positive and negative because we are plotting the log magnitude. So, now if you look at this response, so this is similar to this, the only difference is here the peak was at theta because the pole is at r e to the j theta. Now, this corresponds to theta being 0, and hence if theta varies, if you look at this expression here, if you look at this expression, if theta varies, all that will do is it will shift this frequency response either to the left or to the right, because if you replace omega by omega minus theta, you are going to shift the response, and hence depending upon the value of theta, you will either shift to the left or to the right, and hence this general picture in which we have this particular value of theta. Now, all we have to do is shift theta to the left to make theta equal to 0, because that is what this angle corresponds to, and therefore, the frequency response of this will look like this. And this is a crude low pass filter, because here the gain is maximum, and then when you go along the unit circle and when you hit this point, the gain is minimum, and this is a very crude low pass filter. On the other hand, if you had the pole here, you can expect the gain to be maximum when you are at omega equal to pi, and you can expect the gain to be minimum when you are at omega equal to 0, and hence if the pole were here, you can expect the frequency response to be like this. Therefore, this is a crude high pass filter, this is a crude low pass filter, and both these high pass filters have been realized using a single pole, and of course, you also have a trivial 0 which does not play any role in the magnitude response. Now, on the other hand, if you try to realize a low pass or a high pass filter using a 0, suppose you want to realize a low pass filter, at omega to 0 you want the maximum gain, which means you need to place the 0 as far away as possible, and hence to get a low pass filter, when you want to realize this using a 0, you have to place the 0 here. But now look how the response changes. The response will be something like this. These are rough sketches. And similarly, when you have a high pass filter, the response will be something like this. So, this follows from what we had discussed earlier. So, if you have a 0, the valley is sharp, the peak is broad. Therefore, you see the difference between these two cases. And so, these are qualitative pictures. Now, if you look at some actual numbers, we can think of h of z. Let us look at the low pass filter case. If you are going to realize this using a single complex pole, then the transfer function has to be of the form 1 by 1 minus a z inverse, where I am assuming a is real valued and a is between 0 and 1. Therefore, the pole is at a, so that corresponds to this case here. The pole is at a and I am assuming a is between 0 and 1. So, this is a low pass filter. On the other hand, if I have h of z to be 1 plus a z inverse, the 0 is at minus a, right. Again I am assuming a is between 0 and 1. In both cases I have So, this is a crude low pass filter, this is a crude low pass filter. And if you evaluate the frequency response to get some feel for the numbers, suppose you evaluate this at omega equal to 0, right, and if you evaluate the magnitude squared frequency response at omega equal to 0. So, this will be 1 by 1 minus a whole squared, omega equal to 0 corresponds to z equal to 1, and if a equal to 0.9, then maximum gain is 100 and this is 20 dB. Now, let us look at some other comparison point. Let us look at h of e to the j pi by 2. We are evaluating the frequency response at pi by 2, and remember this is 1 plus a square minus 2a cos omega minus theta. Theta is 0 because theta is angle of the root. Here the theta is on, here when a equal to 0.9, theta is 0. Therefore, this is what the magnitude squared is, and when you evaluate this at omega equal to pi by 2, you get 1 by 1 plus a square. And for a equal to 0.9, this turns out to be 1 by 1 plus 0.9 whole square. So, this is 1 by 1.81 and this roughly is, so it is roughly 0.55. Now, let us look at the case here. If you look at h of e to the j0 whole squared, so this is 1 plus a whole squared, all right, and for 0.9 this becomes 1.9 whole squared, which is 3.61, correct, and h of e to the j pi by 2 whole squared is 1 plus a squared as before, and this turns out to be 1.81 because a is 0.9. Now, if you look at these numbers for the low pass filter realized using the 0, the maximum gain is 3.6. At pi by 2, the gain has, the magnitude squared has dropped to half the peak value. Therefore, the 3 dB bandwidth is pi by 2, because at pi by 2 the magnitude squared has dropped by half. Therefore, you can infer that the 3 dB bandwidth is pi by 2, and for the low pass filter realized using the single pole, you will find that the 3 dB bandwidth is pi by 30. So, this is something you should verify later. In this case, the 3 dB bandwidth is pi by 30. So, this is part of this exercise you need to carry out. So, 1 by 1 minus a z inverse. So, you have find the expression for three dB bandwidth. So, this is h of z. You need to calculate h of e to the j omega whole squared, and h of e to the j omega whole squared is an expression like this. In general, it will be 1 by 1 plus a r squared minus 2r cos omega minus theta, and then you need to find at which point the gain drops by half. Find out what the maximum gain is, and relative to the maximum gain, at what frequency does this drop by half. So, you will be able to get a closed form expression, and you will be able to verify that for the low pass filter case using a pole, the 3 dB bandwidth is pi by 30, whereas for the same low pass filter using the 0, the 3 dB bandwidth is pi by 2. So, this is 15 times narrower, and this also along expected lines, because for the single complex pole, the rough frequency response is like this, whereas a low pass filter generated using a single complex 0, the response will be like this. And clearly you can see the difference in the bandwidth. So, this example shows you that in general poles tend to give you sharp peaks, and that is why when you want to shape the frequency response, if you have poles also to play with, that is if you are considering systems that have both poles and zeros, then you can get very sharp transition from pass band to stop band using poles. Whereas if you have only zeros to work with, as in the FIR case, if you want similar frequency response characteristics, what you will have to do is you will have to increase the order. So, although we have not discussed filter design in any detail at all, just at an intuitive level you can see that if you had both poles and zeros to play with, to get a same or desired magnitude response, if you also had poles, you will end up with systems that have lower order. That is B of z over A of z, you will have polynomials of lower order. On the other hand, if you want to have the same frequency response or roughly the same frequency response, and if you had only zeros to play with, that is you are working with FIR filters, then you will need much higher order to get the same rough frequency response. And this example kind of illustrates, gives you some feel for why this might be the case. So, we are making some general intuitive level statement observations based on this particular example. And you can do this in MATLAB, you can plot this exactly in MATLAB. Maybe it is worth showing this. So, I have each LPF I want, and this is realized using pole. So, this is freak Z. I have B comma A comma N, and the transfer function is 1 by 1 minus A Z inverse. Let me make the numerator as 1 minus A. If I make the numerator as 1 minus A, then I am normalizing the gain, because if I have 1 minus A by 1 minus A Z inverse, then if I put Z equal to 1, I will get 1 minus A by 1 minus A, and the peak gain will be 1. Therefore, so let me make A equal to 0.9, and then numerator is 1 minus A, it is just a constant, so that the peak gain is 1. Denominator is 1 minus A Z inverse. Then I am going to evaluate this at 1000 points. So, this is my low pass filter. Okay. Now I am going to get the low pass filter, but now using 0. The numerator is now 1 plus AZ inverse, A is 0.9, and the denominator, because I want to normalize the gain, the denominator is just a constant, and that constant happens to be 1 plus A, right. So I have low pass filter realized using both pole and 0. Let me. And now let me plot both. So I will plot 0 to, I have 1000 points, and now I will divide by 2000 because I am evaluating this from 0 to pi. If I normalize it by 2 pi, the frequency axis will be 0.5. And then let me plot 20 log 10 absolute value. These are complex numbers, therefore, this is HLPF using pole and LPF using 0. So now you see exactly the picture similar to what I had drawn by freehand. So this blue curve is the low pass filter using single pole. The radius was 0.9, and the red curve is the high pass filter, and this 3 dB bandwidth is clearly much narrower than this, whereas here the 3 dB bandwidth is pi by 2 roughly, and you can also see that here. So pi by 2 corresponds to 0.25, and you see the y value is minus 3.012. So it is 3 dB below the peak value. So in general, poles provide sharp peaks, and hence you can expect the frequency response to be realized with a much lower order filter if you had both poles and zeros to play with, as opposed to playing with only just zeros. To illustrate this point, let me design a low pass filter. This is what is called as an elliptic filter. You will not know the details of this unless you take a course on digital filter design. I will just design the filter and then show the characteristics, the pole zero plot and the frequency response. So this is 5th order elliptic filter. Never mind what these parameters are. And then if you plot the pole zero plot, this is how it looks. So this is a 5th order elliptic filter. These are all the poles and these are all the zeros. And now let me plot the frequency response of this. So this is clearly an IR filter because there are uncancelled non-trivial poles. Therefore, this frequency response is this, and then so this is the frequency response. And if I, here you do not see the ripples on this scale. So, you should see a bump due to this pole, another bump due to this, and another bump due to this. Actually, you will be able to see the bumps if you plot this on a linear scale. Now, you are able to see the bumps in the pass band. Now, let me plot another low pass filter. So, the numerator polynomial is h itself 1 and 1000, and if I now plot this, you can see that these two are very similar. They have roughly the same pass band, transition band, and stop band. But the point is, this is a 32nd order FIR filter. So, this is an FIR filter, this order is 32, whereas this is just 5th order. So, 5th order you are able to get a frequency response that has this pass band, this transition band, and this stop band, whereas you need a much higher order when it comes to the FIR case. And just one last plot, if I so these are the zeros of this FIR filter. So, here the off unit circle zeros govern the pass band behavior, these zeros on the unit circle govern stop band.